Hello everyone and welcome to another lesson for Calculus 1. In this lesson we are going to do some graph sketching, and this corresponds to section 3.6 in the Larson Calculus textbook. More or less, I choose to do this a different way than how the book presents it, but it gets across a lot of the same ideas. So in this lesson, we will be using the first and second derivative to graph functions, as well as some other things like asymptotes or intercepts. Basically some good ideas on how to do all of this graphing without actually needing to find a first and second derivative. So as a reminder, before we go ahead and hop into some examples, if the first derivative is positive, that means the original function is increasing, and that is a left to right movement. And if the first derivative is negative, then the function is decreasing from left to right. Now you can see here that there are two different versions of a first derivative increasing, like this. And that's because based on the second derivative, or the concavity, it can either have increase with a positive concavity, or it can increase with a negative concavity, opening down, opening up. And the same thing can happen when the first derivative is negative. It can be negative or decreasing with a positive concavity, opening up, or it can be decreasing with a negative concavity, opening down. One last thing before I move on here is I want to state that the first derivative can also be represented like this, the first derivative being positive. The first derivative being negative can also be represented like this. The first derivative is less than 0, that forces it to be negative. The same thing for the second derivative. We can say the second derivative is greater than 0 for positive, and the second derivative can be less than 0 if it's negative, just to give it some more context, at least in terms of notation. All right, let's hop into our first example here. Our first example is trying to get us to sketch the graph which satisfies the following conditions. So here we have that f prime, the first derivative is positive on the intervals this one and this one. The first derivative is negative on this interval. The second derivative is positive, the second derivative is negative. The graph contains the point -1, 0, and the graph is smooth. So there's a lot to unpack here. So we have, at least we can say this point right here, this is an x-intercept. And so you always want to look for intercepts, and I think that's what you will want to do first. You want to do any points that you see, you want to do that first. So -1, 0, that's this point right here. I'm going to get that right down on the graph right away because that's probably the easiest thing to do out of this entire list. And so I'm going to come back here and cross that one off. We're done with that one. The next easiest thing to do here is to look at this phrase, the graph of f is smooth. This word right here it means a lot. So smooth means continuous and differentiable on the interval. And so you might be asking yourself, what interval? Well, if there's no interval given, then we assume that it is the interval is all real numbers. So again, with the interval here, we are talking a domain. So the graph is smooth. That means we shouldn't see any cusps or sharp turns in the graph. So or in fact, no discontinuities. So there should be no cusps, no sharp turns like absolute value turns, or discontinuities, no hole in a graph, no asymptotes, no nothing. So then we have to come back and contend with, we're done with that one, we've got to come back and contend with all of these other ones. So you'll notice that we have the first derivative for these 2 points and the second derivative for these 2 points. And so I'm going to move this up a little bit so I can make my table. What's important to do now is that I want to make a table. And I'm going to have a list of x values. And these can include, say, intervals. I will be including f prime of x and f double prime of x. All right. So what is going on here? What x values or intervals do I see up here? Well, I see, first and foremost, in the first derivative, I see -1 and +2. In the first derivative again, I see +2. In the second derivative, I still want to pay attention to what values I see. I see -1 here and here, and I see +1 here and here. So I need to write those values in the correct order down here in my table. So here I go, I will have -1. I'm going to write x equals -1. That is the first value I see in the first and second derivative. Let's see. The next value I see is 1. So I'm going to leave a little bit of space here. X equals 1. And then I have another value in the first derivative, x equals 2. Now in between all of these, I have to get the rest of the intervals here. So I want -infinity less than x less than -1. This is everything to the left of -1. I want to put another interval here, let's say -1 less than x less than 1. You'll notice that this is everything between -1 and 1. So the next interval that I have would be 1 less than x less than 2, and that denotes everything between 1 and 2. And then for the last interval, I will have, let's see, 2 less than x less than infinity. And again, I want to point out here that the only numbers that I'm writing are the numbers that show up in the actual intervals up here for the first and second derivative. So let me finish highlighting here. We went from 1, 1, 1. This was both green and black. That number showed up in both of them. And then 2. So all those numbers came from up here, these intervals. And then we just have to go through and figure out, well, is the first derivative positive or negative or what's going on here? So from -infinity to -1, the first derivative is positive. So positive. At x equals 1, the first derivative is going to be 0. That is what's happening there. The first derivative is 0. Because it's not positive at x equals 1. We had to exclude it. All right, so let's see what happens here. Between -1 and 1, that's here, the first derivative is still positive. At x equals 1, the first derivative is still positive because at 1 is in this interval, and the first derivative is positive in this entire interval, including 1. Between 1 and 2, the first derivative is still positive. At x equals 2, though, the first derivative is 0. And that is because it is not included in this interval or this interval. And finally, between 2 and infinity, the first derivative is negative. And we do the same thing for the second derivative. And again, you can see the only times that the second derivative will be 0 is where the interval stops and starts. So at -1, the first derivative is 0, and at the second derivative is 0. And at +1, the second derivative is at 0. But this x equals 2 is in this interval, so that is still negative. All right, so why are we doing all of this? Well, we can recall the table from the last slide. If the first derivative is positive and the second derivative is negative, it has to be increasing but concave down. So we know it's going to look something like this. For this one, we don't have any actions. But where the first derivative is positive and the second derivative is positive, it has to be increasing and concave up. So it'll be doing something like this. Here's a weird one. At x equals 1, we have a positive derivative, which means it's still increasing, but the second derivative is 0. Let's come back to that in a minute. Here with the positive and the negative, that is something that is increasing but concave down. So that'll be like this. And then the last one that we can deal with that has only signs going all the way across is negative, negative, which means it has to be decreasing and concave down. So what goes on with this pair and this pair? This is very interesting. So the positive nature of this means that the function is still increasing at x equals 1. But if you notice, the second derivative goes from positive to 0 to negative. This represents an inflection point. So I just have to abbreviate inflection point. That is where the concavity changes, and you can sort of see with the little drawings we did over here, it's concave up to the left of 1 and concave down to the right of 1. And something similar happens here. Is there an inflection point here? Oh yeah, there's going to be an inflection point here. Oh man. So let me write that as well. There's an inflection point here as well. And that's because the concavity changed. Now, if we look at this one here, this 0, what we could not identify here, there was nothing here. This is telling us that there is a relative maximum. Because the first derivative goes from positive to negative, that means the function goes from increasing to decreasing. And so this would be a relative max. All right, let's get this drawn up there then. So from -infinity to -1, it has to have this shape. So here I go. From -infinity to -1, it has to have this shape. And I'm going to stop right there. So what we're checking for here at this point is there a horizontal tangent line? Yep. When I finish drawing in this graph, it'll look like there's a horizontal tangent line. And will the inflection change? Well, if I just continue from -1 to 1 and start drawing the graph like this, then yeah, we will absolutely make that inflection change based on just the drawing I made down there. So from -1 to 1, it is increasing and now concave up. and I have to stop at -1 because at 1, the concavity will change again. It'll still be increasing, but now concave down, and I have to start at this point and start making the graph look like this. So from 1 to 2, I can make my graph look something like this. There we go. And at 2, I have to make sure that there will be a relative maximum, and after 2, I have to make sure the graph starts moving down in this fashion. So after 2, I'm going to continue my graph probably something like that. And there we have it. So we have to include where the inflection points are, and this is good enough for me. Here are the inflection points. Just where the concavity changes, and you want to point out where the relative max and min are, if there are any at all. So there would be the relative max. Let's take a look at a couple more examples. I promise they will go a little bit quicker. All right, here's another example. There are some slightly different things going on here between this example and the last one. So let's go ahead and look at all of the characteristics. We have some x-intercepts. We have some first derivative stuff, positive and negative, going on. We have some second derivative stuff, positive and negative, going on. Ooh, we have the inclusion of a vertical asymptote, and the graph is smooth everywhere the function is defined. This means that the function will be smooth everywhere except where there is the vertical asymptote. So we can get the x-intercepts in here, and we can get the vertical asymptote in here. There we go. There's the vertical asymptote, and the x-intercepts are at -1 and 2. So this smooth everywhere the function is defined means that to the left of this vertical asymptote, there won't be any cusps or discontinuities or sharp turns. And the same thing to the right. But we do have this discontinuity, and that's okay. We already have that taken care of. So let's take a look at the first derivative stuff and the second derivative stuff, and I will create a table down here, much like I did in the last slide. All right, here is the entire table with all the little intervals that are there. And I'm going to highlight again very quickly. Let's see, the -1. The only numbers that show up in this list are the numbers in the interval above. So -1, 1, 1, 1. And then in the second derivative, we have all of these numbers. We've got -2 in our interval here, -2, -2, +1, +1, +1, 2, 2, and 2. All right. So we have all of these numbers here in this list where the x's or in the intervals show up, showing up in these intervals here. They all represent x values. So we can then get a picture for what this graph is going to look like. If you're decreasing and negative, the graph, decreasing and concave down, the graph looks something like this, decreasing concave down. When the function reaches x equals 2, the function will still be decreasing, but there won't be any concavity. Let's take a look at the next one. Yep. The concavity changes at x equals -2. So that means this will be an inflection point. I'm just going to abbreviate IP, inflection point. Since here the the first derivative is negative and the second derivative is positive, that means we have to be decreasing but concave up. So it should look something like this. And then here at 0, anytime you see a 0, you need to look at the signs on both sides of it. So here at 1 and here, to the left of -1 and to the right of -1, the first derivative sign changes. Let's see, so the original function would be decreasing and then it would be increasing. So that would make this a relative minimum. And the relative minimum would be at x equals 1. Cool. After x equals 1, between -1 and 1, which is where the vertical asymptote is, the graph is increasing and concave up. So something like that. Then we have this new thing. At x equals 1, the derivative and second derivative are undefined, and that is because there is a vertical asymptote. But on the other side of the vertical asymptote, we have this idea that, I goofed a sign here. This should be negative. There we go. So we have this negative first derivative and positive second derivative, which means it has to be decreasing but concave up, so doing something like that. So take a look here again. I have another 0. Look on the signs of both sides. Do the signs change? Yes. So that means there would be an inflection point here. And in fact, I goofed all of these signs. All of these signs here for the first derivative are negative. There we go. And then lastly, we would have a decreasing interval that is also concave down, which would look something like that. So then all we have to do is plot this thing between negative, let's see, how do I want to do this? Between -infinity and -2, we have to be doing something like this. And I know that I have to be above the x-axis because this is a relative minimum. So we cannot go below this value here. It's got to bottom out right there. So I've got this relative minimum here. In between -2 and -1, I'm making my graph look like this. You can see I did it there. But then after -1, I have to make it creep back up. And it looks like that would naturally happen as we get closer and closer to the vertical asymptote. So here we go. There's that. So I already had marked here an inflection point. And here we have a relative min. Awesome. So then at x equals 1, it is undefined, but we can start to the right of x equals 1. We have to be decreasing but concave up, so the graph should look like this as we come down. But I know that the graph has to start up here, because as we come down, there has to be an inflection point at x equals 2. We already know from up here as well that the x-intercept is at 2, so the graph has to pass through this point. So let me get that going here. We are decreasing and concave up. There we go. And at that point, the concavity has to change, and we can still decrease and move down forever. So one more inflection point right here. And that's how you label it. You just draw an arrow, say, hey, that's a relative minimum. Hey, you draw an arrow, hey, there's an inflection point right there. Maybe you want to put some emphasis on it, like right there's the inflection point. Right there is the inflection point, so that people know where it is. All right, I've got one more example of graphing, and then I want to get into the graphs of functions and their derivatives. Not just using their derivatives like this, but how to find the derivative of a graph. So here, this is the last example I have for this particular part of this lesson. Why don't you try this? Try it, write it down, get yourself a poorly drawn coordinate plane, and see if you can work through this one and get a graph. So here is the graph for this particular function. You can see that the first derivative is positive from negative infinity to 2. So I have this graph increasing the whole time. Second, you can see that the first derivative is negative after 2. So that means the graph from left to right will be decreasing. F double prime is positive from negative 1 to 1. That means it is concave up here to here. And it is concave 2 to the left of negative 1. Yep, it is concave down, and it is concave down to the right of 1. Also concave down. The graph is smooth. So where are these extrema? Well, we have a, what is this? We can say a relative maximum here. And in fact, this is also going to be qualified as an absolute maximum. We could qualify it as an absolute maximum if you wanted to. But the direction says just to be sure to label all relative extrema and inflection points. So this would be the extrema. There we go. And then the inflection points, I will just abbreviate IP again, inflection points. That is where the concavity changes. We know that the concavity changes up here at -1. It goes from being negative to positive. And then again from at 1, it changes from positive to negative. So we have these two inflection points right here and right here. So this section gets a little abstract, but we will be looking at the graphing the derivative of a function. So what's going to happen is you will be given the graph of some random function, and then you will be asked to graph the derivative. So the first thing that I think really makes sense is that you want to take note of any critical values, and then you plot those as x-intercepts. You plot those as x-intercepts for the derivative. Remember, you can find critical values when you set the first derivative equal to 0. So if you find any critical values on your graph, that means the derivative is equal to 0. And I will address when a derivative is undefined when we get to that example. The next thing that you want to do is you want to use the intervals where the function is increasing or decreasing to sort of give yourself an idea what the graph of the derivative is doing. So if the original function is increasing, the derivative will be above the x-axis, and if the original function is decreasing on a given interval, then for that entire interval, the derivative will be below the x-axis. All right, let's see if I can do this. Here come some examples. On this slide, I have a couple examples here, and we will be making sure that we find the derivative just graphically of these particular examples. So for all of these, I will do the derivative in this green color here, derivative. So the derivative is green, and any other graph you see is the original function. So the first thing I want to do, especially with this first example, f of x on the left, is I want to find out where are the critical values. And the critical values, again, are where the function has a tangent line with a slope 0, or where the original function is going to be undefined. And wherever these critical values are, that's going to be a 0 on the x-axis for the derivative. Now, the next thing that we have to figure out here is, based on these critical values, in this case we just have 1, what is happening to the left of this critical value and what is happening to the right of this critical value? Since the left side is decreasing, that means the derivative will be beneath the x-axis that way. Now, to give a better understanding as to what's going on, this green line here is representing the slopes of the tangent line along this particular interval of the original function. So as you can see, if we just move over just a little bit, the slope of this tangent line will be negative. Let me highlight this with a yellow dot. This point right here, the slope of this tangent line will be negative, but not by very much. And you can see that the value here is not that far below the x-axis. But as we start moving further and further and further left, and I get to say this point here, I'll mark that with a blue dot, maybe this point here, you can see that the slope of the tangent line here is going to be much steeper in a negative direction. That's why, if we follow this straight down to our graph, this number is much more negative, it's further down the x-axis than this number here. So that's how you think of it as you're going along to graph it. And let's see, to the right, this will be slightly positive at the beginning because the slopes of the tangent lines are only a little bit positive. And then as we keep getting further and further and further right, the slopes get bigger and bigger and bigger and bigger. So we will just increase forever. And it also makes sense again that since the original function is increasing there, the values of the derivative are positive and they keep growing. Now, to give this a little bit more context as well, anything that is quadratic will turn into something that is linear. So let's just say f of x was this. No, it was x squared minus 4, say something like that. If you found the derivative of this, it would just be 2x by the power rule. So you can see there we have this 2x power, or 2x derivative, which is just a linear function. And this is going to happen all sorts of ways. So this is a cubic function. And if we want to find the derivative of a cubic function, it'll have to be quadratic. So let's try this process again here. I'm going to find the critical values as I can. And really, we're just looking, more or less, just looking for maxes and mins. That's where critical values are going to happen. So there's one tangent line of 0. Here's another tangent line of 0. So we will have two x-intercepts for this graph, right above and right below this particular extrema. Now, next, you may notice that in between these two, the graph is increasing, which means the derivative has to be positive, which means that between these two x-intercepts, it'll be above the x-axis. Let's go. And since to the left of this x-intercept on the derivative, to the left of this relative minimum, the function is decreasing, and we would have to make sure that the derivative is negative, aka below the x-axis. And the same thing over here, from this relative maximum, if we go to the left, the function is decreasing, which means the first derivative is negative, which means it would be below the x-axis. So here is the derivative, whoops, that's p prime of x. There we go, p prime of x, and this green graph over here would be f prime of x. All right, last couple examples here. We already understand things like this minimum and this maximum, and that those will give us zeros on our derivative. So like right there and right there. And those zeros for the derivative happen directly above any maximum or minimum. Except we have this right here. This is also a critical value, but the function goes from decreasing to decreasing. So not all critical values are easily spotted like this one here or this one here. You have to take a look for maybe where does a change of inflection happen? Where does the concavity change? Where are there inflection points? Because there being an inflection point could possibly give you another critical value. So how does this work? From left to right, this function is decreasing, which means the derivative would have to be below the x-axis. So something like this here. There we go. But then to the left of this, it's still decreasing. So that means it has to be moving down, but it has to come back up to this x-intercept here. Because in between these two extrema, the graph has to be above the x-axis because this is increasing from left to right. So it looks something like that. Whoops. Looks something like that. There we go. But then to the right of this 0, the function goes back to decreasing, which means the derivative would have to end up back under the x-axis. So here we have g prime of x. And lastly, over here in this example, the only thing that's new is this vertical asymptote. Guess what? In the derivative, there would also be a vertical asymptote in that same place. So here, just pretend it's right there. We have that weird point like we had over here in this example, where there is a zero sloped tangent line at that point, but there's no extrema here. So this graph from left to right is increasing. We have a zero slope tangent line, and then it's increasing after that. So that's what the left side of the vertical asymptote looks like. And again, we have on the right side of this vertical asymptote an extrema here, in this case a relative minimum, which would be here. So from the vertical asymptote, the graph is decreasing. So that means from the vertical asymptote, it has to be below the x-axis. In fact, it has to tail off toward the vertical asymptote there. But after this value here, the graph, the original function is increasing again, so we know to the right it will be positive. And that is h prime of x. And just so you know, these are very much sketches. These graphs are not very accurate at all. It's just trying to get you to think about how would the graph of the derivative look based on just some function. And you may notice too that I had no x-intercepts here at all, or no coordinates where there were relative extrema or zero slope tangent lines. You can just line everything up underneath or above where those extrema and critical values are. And that wraps up the lesson for 3.6. I hope you have a better understanding of how to graph given some characteristics and find the derivatives of some graphs. Good luck.